Okay, here are the notes for section 5.6, the law of cosines. So here's our law of cosines. A squared equals b squared plus c squared minus 2bc cosine a. So if you notice, the pattern actually holds. To any side squared is equal to the other two sides squared added up minus twice the product times the cosine of the angle you're trying to find. So pretty much, given this information, you're just plugging things in. So once again, we're solving triangles, so finding all the values. Now, the reason that you may need to use the law of cosines is that law of sines only works if you know a side angle pair. If you don't know a side angle pair, you cannot use the law of sines. So cosines kicks in if that's the case. So for example, if you look at this one, a is equal to, whoops, don't know a, don't know b, don't know c. A little a is 11, a little b is 5, and angle c is 20 degrees. So here, the reason I can't use law of sines is that I don't know angle A or angle B, so I can't use these sides, and I don't know side C, and there's no way to find it. Now, you may be tempted to Pythagorean theorem, a squared plus b squared equals c squared, but you don't know this is a right triangle. It probably isn't, in fact. So Pythagoras doesn't hold. Also, that's not the right angle, so that's not the hypotenuse anyway. So, however, usually use law of cosines if you have two sides that are missing the third. Because if you look at my formula for little c, I need side A, side B, and angle C. I have side A, side B, and angle C. So I can start with this c squared equation. So c squared equals a squared plus b squared minus 2 times a times b times the cosine of my angle. And I can literally just type that whole string into my calculator. Now, so let's see here, 11 squared plus 5 squared minus 2 times 11 times 5 times the cosine of 20. So gives me that number. Now that's c squared, so I do need to take the square root. So c is equal to about 6.5. So there you go. There is c. Now I can actually use these formulas to find angles as well. It just takes a little bit more algebra. So let's find angle A, for example. So this is the equation that has angle A, so I'm going to use this equation. So for angle A, it's a squared equals b squared plus c squared minus 2 times b times c times the cosine of angle A. So algebraically, what happens, and we can actually jot this down up here, the cosine of any angle is equal to -2, in this case, BC. So, or if you don't like all these negatives, b squared plus c squared minus a squared over 2 BC. So the cosine of any angle is equal to the square of the sum, or the sum of the squares of the other minus the one you're looking for, divided by 2 BC. It's just a rearrangement of this. So you have to do the same thing for the other one. So cosine B, for example, that would be a squared plus c squared minus b squared over 2ac. Cosine C would be a squared plus b squared minus c squared over 2ab. So if you notice that the one that's being subtracted at the end always matches the angle, and the 2 on the bottom are always the other 2, whatever the first 2 are here. So for this, we can rewrite this. So the cosine of A is equal to b squared plus c squared minus a squared over 2bc. So let's see here. B squared, now this one you might be careful and typing more than once. So here's b squared plus c squared minus a squared divided by 2 divided by b divided by c. Now notice this division's everywhere. Don't do 2 times 5 times 6.5, because that actually only divides by 2 and puts the 5 and the 6.5 in the numerator with all of this stuff. So that is what the cosine of A is equal to. So to get what angle A is actually equal to, I'll need the inverse cosine. So angle A is 145.8 degrees. So fill in 145.8. And now I can actually don't need to do any more fancy math, because now that I know two angles, I can do angle B because it's 180 minus the two angles. So 180 minus 145.8 minus 20. Whoops. Now I've done it. 180 minus 145.8 minus 20. So B is 14.2 degrees. So there you go. The farther you round this, the more exact your angles will be. So if you don't get exactly the same numbers I do, is probably where we round to. Okay, so this also works if I know all three sides. So angle A, angle B, angle C. Little a is 9, little b is 7, little c is 5. The reason you can do this is that your angle equations only require sides. So let's find angle A. So the cosine of A is equal to b squared plus c squared minus a squared over 2 times b times c. So 7 squared plus 5 squared minus 9 squared. So that's my numerator. Divide by 2, divide by 7, divide by 5 is that, and then take the inverse cosine. So angle A is about 95.74 degrees. So fill it in, 95.74 degrees. Repeat the process for B. The cosine of B is equal to a squared plus c squared minus b squared over 2ac. So 9 squared plus 5 squared minus 7 squared. Divide by 2, divide by 9, divide by 5. Take the inverse cosine. Angle B is 50.70 degrees. And now that I know two of my three angles, I can do the 180 trick to get the last one. Angle C is 180 minus 95.74 minus 50.7. 180 minus 95.74 minus 50.7. So C is 33.56 degrees. And there's my solved triangle. Alrighty, so you also get some interesting formulas because of this. So this is the area of a triangle. This normally you do 1/2 base height, but if you don't necessarily know the height, but know two angles, or sorry, two sides and the included angle. So included angle means angle A is the angle between sides B and C. If you notice, this angle is the other letter that's missing here. So here it says find the area of a regular octagon. So that's a stop sign. Regular means all the sides are the same length. Inscribed inside of a circle that has radius 9. So the thing about an octagon is we're actually looking at this, for example, triangle. So these two sides are 9. The angle in between, since this is an octagon, I can figure out what that angle is. That angle is 360 divided by 8, which is probably 45, but just to make sure. Sure is. So 45. So I have two sides and the included angle. So the area is equal to 1/2 the product, whoops, not 8, the product of the sides times the sine of the angle. So 0.5 times 9 times 9 times sine 45. So the area of that wedge is 28.64, we'll call it. Now, the thing is, that's one wedge, but it's an octagon, so there's 8 of these. So the full octagon is going to be 8 times that value. So multiplied by 8. The area of the whole octagon is about 229.10 inches squared. Because my radius is measured in inches. Okay, Heron's formula. Let A, B, and C be the sides of angle ABC. So you can. This is how you can find the area of a triangle if you know all three sides of it. Doesn't matter if you know the height. The thing is you have this S value, which is equal to the sum of the sides divided by 2. So find the area of a triangle with sides 13, 15, 18. So the first thing I need to do is figure out what S is. So 13 plus 15 plus 18 divided by 2 is 23. And then I just fill in the formula. and then let my calculator handle the rest of it. So let's see here. Yeah. So the area is equal to the square root of 23 times 23 minus, well, it's the first side, 13, times 23 minus the second side, which is 15, times 23 minus the third side, which is 18. So this is the square root of 23 times 10 times 8 times 5. 23 times 10 times 8 times 5 is 9,200. And I just take the square root of that number. So the area of that triangle is 95.92 units squared. So just plug in the numbers in the formula. Okay, so let's do some applications here. So a baseball diamond is a square with, that should be dies, sides of 90 feet. So, if you think about a baseball diamond, it looks like this. 90 feet from home plate to each base, or base to the next one. The front edge of the pitching rubber is 60.5 feet from the back corner of home plate. So 60.5. Find the distance from the center of the front edge of the pitching rubber to the far corner of first base. So this is what I'm looking for. So let's pull our little triangle out. So we've got this triangle. Now notice that's not actually a right angle, just so you know. So that's why I can't assume that that is the case. So I do know that this angle is 45 degrees. I know that this distance is 90, and I know that this is 60.5. So I'm trying to find this distance here. So we'll call this side A, we'll put B here, we'll put C here, which means this is little a, this is equal to little b, this is equal to little c. So let's write down our info from our triangle. So A is 45 degrees. Angle B, I don't know, and angle C, big C, I don't know. Little a is 60.5, little b is 90, and little c is what I'm looking for. So I have two sides and one angle. So let's see here. What can I figure out? Oh, no, I put it in the wrong place. I don't know little a. That's what I'm solving for. Little c goes down here. Okay, but I have a formula from the law of cosines that lets me find this exactly. I'm looking for a. So the formula for a is a squared equals b squared plus c squared minus 2bc times the cosine of a. Just fill in the values. So a squared is equal to 90 squared plus 60.5 squared minus 2 times 90 times 60.5 times the cosine of 45, and that all just goes to my calculator. So 90 squared plus 60.5 squared minus 2 times 90 times 60.5 times, 60.5 times the cosine of 45. That's going to be wrong because that's just a nut. There we go. 90. So all that in is, that's a squared. So a squared is equal to 4059.857153. Then take the square root. So a is 63.72 feet. So there you go. The distance from first base back to the center of the pitching mound is about 64-ish feet. So it's actually slightly farther from the mound to first than it is from the mound, 4 feet actually, about, from the mound to first, the mound to home. So the pitching rubber is actually not in the center of the diamond. Okay, example 6. Regular tetrahedron is a solid with 4 faces. Each width is an equilateral triangle. Find the measure of the dihedral angle formed along the common edge of 2 intersecting faces of a regular tetrahedron with length 2. So it's kind of a drawing this picture is going to be tricky because it's a 4-sided die essentially. Okay, so what can we figure out here? So the edges are 2. So if I do that, that's 1 and 1, which makes, let's see here, that dotted line distance is root 3 because that's a 30, 60, 90 triangle actually. So let's see here, and that's also true for the height of any side. So find the measure of the dihedral angle formed along the common edge of two intersecting faces of a regular tetrahedron. So that would be like the angle between the bottom and this right-hand side or something like that. So this, we can put the dashed line in here as well. That dashed line is also root 3 because for a regular tetrahedron, all the sides are the same face. So let's see here, and we know this edge is 2, so we actually know, so we'll call that's our angle we're looking for. So angle A, angle B, angle C, little a, so we'll call the angle we're looking for, we're going to call angle A. So the side across from it is 2, little b is the root 3, little c is also root 3. Now, since I'm looking for a, I can use my cosine A formula. So that is b squared plus c squared minus a squared over 2 b c. So this is 3 plus 3 minus 4 over 6. When you square the root, it just goes away. On the bottom here, root 3 times root 3 is the same thing as root 3 squared, or it becomes root 9, which is 3 times the 2. So the cosine of A is equal to 2 over 6, or 1/3. So I need to take the inverse cosine of 1/3. Don't use 0.3, put the actual fraction in. Oops, put an extra 0 in. So the angle A is equal to about 70.53 degrees. Is your angle between two faces of a regular tetrahedron. And that is the end of the section.